Free body diagrams are a nice way to draw the scenario when you're doing a physics problem. So free body diagrams basically will highlight all the forces involved in the actual question that are acting on an individual mass. Now we call them free body because they are separate from any surface they might be connected to or any other auxiliary mass that it also might be touching. So free body diagrams really pinpoint what forces are involved uh, in the question. So if I am to be blunt about it, we like to keep our free body diagrams nice and simple. Cars are going to be a square or a circle. A human will be a square or a circle. Anything that involves mass, just keep it nice and simple. Don't try to overly complicate it. We use vector arrows to represent the forces, and we typically do everything with vector addition. So for instance, this book sitting on the table has two forces acting on it. The free body diagram of this book would be fairly straightforward, right? So the book's not that hard to comprehend as a square. It has mass, and so therefore it has weight. So typically we draw the weight on it first. More often than not, weight's going to be part of almost every single one of these free body diagrams. The only time it probably wouldn't is if we're looking at it from the top. So this is a side view, if you will. So the book does have weight, so pulling it down, the force of gravity, but it's not accelerating. So right now, the way I have it drawn is it's an unbalanced force. Whenever you have an unbalanced force, you have an acceleration. So since a book sitting on the table is not accelerating, it has to be balanced with another force. So that's where the normal force comes in. The normal force is just a perpendicular force acting from the surface that any mass is sitting on. So if you're standing on the ground, the normal force would be acting against your feet, pushing back up on your body. So normal force is sometimes also referred to as the apparent weight whenever you're doing elevator problems, or if you are in a vessel that is moving upwards or downwards or even at an angle. The normal would be the weight that you experience, not so much the weight that you have. So for this problem, that's really all there is to it. When you have balanced forces, we tend to call them conservative forces. And when you have balanced forces, so the forces going up is equal to the forces going down, or the forces going to the right is equal to the forces going to the left, we call that a static state. So that's because all the forces cancel each other out and there's no overall acceleration. In this scenario, there's only two forces, one going down, one going up. And since it's not accelerating, those two forces must be equal in magnitude. So if your weight was 5 newtons going down, the normal force would be 5 newtons going up. So opposite in direction, but equal in magnitude. There's no vector arrows drawn here over Fg or Fn, like there's no vector arrows, so I'm just referring to numerical values, right? If I talked about the vector values of them, your weight in vector notation would be equal to the negative of the normal, because they're acting in different directions. Anyhow, so if you had two people pulling, one person pulling on a box, one person pushing a box, you'd have a slightly different scenario. So this question says, find the acceleration if the two forces are 200 and 300 newtons, friction is 150 newtons, and the box has a mass of 500 kilograms. That's a very large box, but then again, the box is as big as these two gentlemen. So right off the bat, we know there's going to be an acceleration. So this is a dynamic situation. There is an actual acceleration, right? Your acceleration is not zero, which means the forces acting to the right are not going to be equal to the forces acting to the left. I'm assuming the forces going up and down are balanced, because if they're pulling a box across the floor, the box isn't suddenly going to fly up into the atmosphere, nor is it going to crash through the ground. Well, you would assume not. So therefore, we're not even going to bother looking at the forces going up and down. We're going to deal with the forces going left and right, because that's ideally where it's going to accelerate. So we're going to always keep our forces in the X and Y separate. When we find our net force, recall the net force is the sum of all forces, right? Add all the forces together, which is equal to your mass times your acceleration. And one more time, we're going to just mainly look in the X direction. So when I draw my free body diagram, I'll include the y direction, right? If it's a box, it has mass, therefore it has weight, so therefore FG, it's going to still be part of it, even if we're not going to use it in the math. And therefore, if it's on the ground, it has to have a normal force. Just be familiar with always putting that in. It'll come up eventually, where you'll actually have to calculate it. So we have one guy is pulling with a force 1, so that's this guy right here. He's pulling it to the right, so I'll add that force on there. The other guy is pushing from the left, but he's pushing it to the right. So I see this every once in a while. Don't do this. Even though this guy right here, I'll give him a smiley face, is pushing to the right, the fact that he's on the left side means nothing. Because he is pushing to the right, this force right here should be on the right-hand side. So I line things up to the center of mass. Technically, this is the proper way to draw the forces. You should put one vector arrow right after the other. I tend to do it a little bit differently, but I'll show you that in a second. So the two forces are being acted on this box are pushing the box to the right. So both force 1 and force 2 should be on the right. The other force involved is friction. So we know by definition friction's an opposing force. So we draw that going to the left. Okay. So working in the x direction, we know that from over here, the net force is the sum of all the forces. So in this case, in the x direction only, we have applied force 1 plus applied force 2 plus our force of friction must be equal to your mass times your acceleration. Now, all of those are vectors, and you're always doing vector addition. So that's why we're adding forces. The force vectors, we know eventually when you plug the friction in there, it's going to be a negative number. So typically, I wouldn't put the forces one after the other as I had it drawn a second ago, or a second ago I had it drawn looking like that. I would typically just put them really close to the center mass, and that's mainly to save paper space, right? Because sometimes you might have 3 forces and it gets pretty long afterwards, right? So often you just draw them both pretty close to the center of mass and then just call it a day and move on. So to solve this problem, I'll read it one more time. Find the acceleration if the two forces are 200 and 300 newtons. Friction is 150 newtons, and the box has a mass of 500 kilograms. I got ahead of myself with reading. So we got our 3 forces and we know our mass. So we could calculate the box weight, but we don't need it because, again, we're assuming that it's up and down or equal, so we're not going to bother with the normal and the actual weight. All right, so if we clear up some space, we have room to actually start writing. If we make our positive direction to the right, then and label our actual forces accordingly. So if positive is to the right, then therefore force 1's a positive value, force 2 is a positive value, but force friction is a negative value. So if I write our problem to the left here, input in all of our forces. Force 1 is 200 newtons plus 300 newtons. Force 2 plus our, again, negative 150 newtons for our friction. I have to stress this over and over again. Just because friction is positive in the actual question doesn't mean it's positive in the math. Friction is always negative. All right. So our mass is 500 kilograms. So we put that in there, and then you just math it from this point on. All right. 200 and 300 is 500. 500 minus 150 is 350. Then just divide both sides by your mass. Oh, first recognize that a Newton is a kilogram meter per second square. Then when you divide both sides by your mass, your kilograms cancel out, and you should be left with a meter per second square. So 350 divided by 500 gives you 0.700 meters per second square. So not a great acceleration, but it is a heavy box after all. So that's kind of the rundown for free body diagrams. You're going to be doing a lot of free body diagrams from this point on, especially when you get into statics. But for now, try to incorporate them if possible in some of those questions between 27 and 30. I know some of them is basically F is equal to MA, and you're probably not going to draw a free body diagram for those, and that's fine. When your questions get a bit more complicated, the free body diagrams really point out all the forces that are involved and how to actually balance them. So if you have any questions, send me an email, and I will talk to you in a while.